to the first ever panel event that we have for new SDR, not new SDR. Shame on me. The SDR-Boston user group, or SDR-Boston. So my name's Alex Wyglinski. Today we're kicking off our first inaugural event outside of new SDR, which is the New England Workshop on Software-Defined Radio, which this year will be its 11th showing. But this is not that. This is not new SDR whatsoever. This is sort of what we've been planning for a few years. And now with everything virtual, this is a great time as any to try out a few really cool topics that may not take a whole day, but is niche, is something very relevant, something very timely, and something very helpful to our community. So what I'll do is I'll actually give a sort of a quick presentation about who we are, all right? And if my toaster of a computer can actually share slides. So, there we go. Second try. So first of all, what is SDR-Boston? So we are a collection of SDR enthusiasts ranging from novice to experts in the New England region. But of course, with all this virtual stuff, well, hey, the world is our community, right? So this is really cool. So we have now this multiplicative factor that, sure, we have a New England flavor to everything, but we really try and bring together everybody from around the world to talk about SDR and all that cool stuff. And we're really interested also in exchanging ideas, networking, and sharing the latest insights on this technology. Today's panel is case in point. Great opportunity to learn more about how to do SDR in the classroom, right? Obviously, pretty much everybody knows us for our annual shindig, which we call New SDR, or New England Workshop on Software-Defined Radio. But there's more to us than just that. And today is the first of what we hope will be many such events. And we're also testing out these virtual environments, not just a streaming Zoom session or YouTube live session, but also, very importantly, the ability to interact with each other, in this case, through something called GatherTown, right? So again, we're not workshops, we're not events, we are a community. Of course, a very whimsical community. When we're not socially distancing, this is exactly how we look. When we are socially distancing, it'll just be this, but in little Zoom boxes, okay? And in terms of organizers of the SDR-Boston sort of gang, there are several folks. There's myself, there's Mike Rame from UMass Boston, there's Neil Pandia, that's an actual life-size portrait of him from Edis Research and NI, John Swoboda from MIT Haystack Observatory, and Yusuf Naderi from Northeastern University. So the purpose of today's panel, it's very, very important, more so than ever, that there is a growing need not only to kind of learn sort of this is how, I learned this 50 years ago, how to do digital communication, so therefore it's good enough for everybody else. There is a need to do more hands-on learning and sort of that practical real-world insight on how communication systems work, right? And there are a lot of tools that are emerging out there, both hardware and software, that are now becoming more and more accessible in terms of cost and functionality and practicality that our future engineers can learn in order to sort of absorb what communication technology is and deploy it in the real world, right? So this is what people think of normally when you think of traditional comms education. And this, of course, these are my chicken scratches from my own software-defined radio undergraduate course that uses software-defined radio in the classroom. This is what it actually is. It's more than just nice little block diagrams, beep, bop, boop. There's a lot of imperfections. There's a lot of real-world phenomenon that needs to be characterized. And the only way to know it is to be thrown into the field with these devices, right? And the title, I think what I sort of kick things off with, the communication theory is more than just I and Q. All these imperfections, these phase rotations, the multipath propagation, and also the hardware and its capabilities. What's bandwidth? What's sampling? What are all these kind of phenomenon? It's very important to kind of understand what the heck is going on, right? So these are actually some chicken scratches, more chicken scratches, but this one on paper and in scan, again, from this past semester of my undergrad SDR course. And this is me trying to explain FSK and the phase rotation of FSK, right? And that was an insightful moment. And oh yeah, by the way, we teach in 7-week terms. So it's a lot of fun trying to teach SDR in 7 weeks. So Really, really, really honored, really excited to have 3 educators of communications that use SDR in the field, and more importantly, putting students into those fields to use them to learn, right? This is kind of a big deal. We have with us Professor Cory Prust from Milwaukee School of Engineering. Okay, we have Professor Fraida from New York University, and we have Professor Marc Lichtman from University of Maryland, College Park. Excellent. So what we'll do is the format is 15-minute presentation for each, kind of like, this is what I did in the classroom. These are my lessons learned, how to and how not to teach SDR in the classroom, right? To teach undergraduates or graduates or whoever, but teaching using this powerful tool. We'll then have the networking session and also Q&A in GatherTown, okay, after these 3 presentations. So we hope to finish at about 2:55, the presentations, and then networking afterwards. So with that, don't forget, please connect with us. Okay, we have an active Slack channel and a LinkedIn page. And you can find out more information about us and future new SDRs and past new SDRs at www.sdr-boston.org. So with that, I am going to turn the floor over to Professor Fraida to kick things off with respect to learning SDR in classroom lessons learned. So with that, Fraida, please take it away.
Great. Thank you so much. Can you share my screen? See my screen okay? Perfect. Okay. And just for those following along in GatherTown, I just want to mention that I have that GatherTown session open at the same time. So if you have any comments or want to ask any questions as I'm speaking, you can pop open the chat window there and make sure your message is addressed to everyone, not only those nearby. And then you can type in questions or comments there and I'll see them during our presentation. Hey, okay, so my presentation is called 1024 Ways to Teach with SDR. And Alex, I really like that example you just brought up about making IQ more concrete, because I felt like I personally didn't really understand IQ at a gut level until I was actually teaching with SDR, let alone using it. I didn't really get it, like in my kishkas, as they say, until I was trying to figure out how to teach it and how to make it real and concrete to my students. And that's one of those things that until you touch it and play with it and try and figure out how to make it real to others, you don't really get it. So I'm going to start by telling you about the course that really did that for me. And this course was actually inspired by the very first DARPA Spectrum Challenge. There have been more recent DARPA Spectrum Challenges, but this one took place in 2013 to 14. And I actually participated as a team that did not do especially well, but I participated nonetheless. And the idea behind this was to create a radio design using software-defined radio, of course, that communicates successfully in non-exclusive spectrum. So either competing against another radio or trying to collaborate with an unknown radio design. And my team did not really do well in the Spectrum Challenge at all, but I did think to myself, hey, this was a really good experience to participate anyways. I learned a lot, and I think I should make this into a course. So that was a crazy idea, but what do you know? I did it anyways. So the first step was, of course, to convince my department to let me try it. And they agreed a year later to let me offer special topics in wireless communications, software-defined radio lab course. And then, of course, I had to convince students to sign up for this kind of torture. But I did get a decent showing. And next, I had to construct my challenge arena. So I wanted to design a course that as closely as possible mimicked the Spectrum Challenge environment, where my students would develop radios that would then compete head-to-head. So I set up this little test bed with 5 radios. 2 radios are designated transmitters, and each of them have a kind of T that connects to both the antenna and to another monitor receiver monitor. And then I also have a couple of designated receivers. So now I have this testbed environment where students can control either one or both TX-ARX peers. And we also have kind of a separate monitor node that's hardwired to the transmitter node that can see everything that's going on and being sent from there. So this is what it looked like in real life at the time. It's moved like to 4 separate buildings since then, but this is still actually live in existence And you can go and use it today if you wanted to. And then I was ready for my students to start. So I come in on the first day and I tell my students, we're going to have these 3 open-ended challenges. The first challenge is to design a radio to communicate over a channel with no interference. The second challenge is to design a radio to communicate over a channel with a known interferer. So I gave them an interfering radio in advance, and they had to design a radio that could adapt and communicate in the presence of that interferer. And finally, we ended with the classic spectrum challenge tournament, communicate over a channel with an unknown interferer. So in that last challenge, all of the student designs went head to head against one another to see who could get the most data through. Now, my students thought challenge number 1 was going to be easy. Communicate over a channel with no interference. That's easy, right? Well, this was way more challenging than they thought it would be. And this was just a great opportunity to teach them all kinds of things that they might not have been so interested in otherwise, but they suddenly realized that without even understanding the basics of the radio architecture, the transmitter and receiver impairments that Alex mentioned, it's not even that easy to design a radio for a channel with no interference. And then, of course, once they got past that stage, they were able to work on their radios to communicate against unknown interference. We ended off with this tournament challenge at the end of the semester where every student submitted their radio design in advance. And I pre-ran the tournament. So I put each pair of designs against another pair in these tournament brackets. And I recorded the output as seen by the monitor and also the data transmitted successfully by each radio. And in our last session of the semester, I played this back to the students. So it looks something like this, where we watched each head-to-head challenge in the entire tournament bracket one at a time. It was very exciting, very suspenseful. I had a blast. And I think overall the course was very successful also because, not only did I have a blast teaching it, but my students also, I think, really came to appreciate wireless communications at a deeper level as a result of this course. Some of them actually went on to participate in other kind of non-coursework spectrum challenges. So you can see here a team of master's students who were in my class then went on to participate in this spectrum challenge hosted at Virginia Tech and won a $1,500 prize as a result. So it was a great class. Now, I've never taught it again. It was way too much work. And I don't think I ever will teach it again. But what I came to realize as a result of teaching this course was that this is really only one way to teach with software radio. So I came in thinking, I'm going to teach a course that's all about SDR. I had students that already had coursework in wireless comms, DSP. I just wanted to make the experience concrete, teach them about like real hardware, real radio impairments. I wanted them to spend time not only programming, but also trying to figure out how to evaluate their designs. And I made a lot of decisions based on kind of what I was familiar with already, but I realize now in retrospect, I could have even taught the same class many different ways. And so since then, I've actually used software radio in the classroom in many other ways that were much less work intensive for me. I'm going to give you a few examples. So this is an example I do every single year in the undergrad computer networks class. So this is not a wireless class. Students don't necessarily have wireless background at all. But in the textbook we use, which is a Stallings bottom-up textbook, they do go through this concept of the relationship between spectrum occupancy or bandwidth and time to transmit a unit of data. And so I love this homework assignment because I make students log on to a software radio that they access remotely over the internet. And then I make them send a bunch of data, just random data, using different data rates, different constellations. And they get to see in a really concrete way, like, hey, you can send it faster using the one on the bottom, but look at how much more spectrum it takes up. Another great example that has nothing to do with wireless comms at all. If any of you teach digital logic, a classic example there is a linear feedback shift register. Well, many students are actually very interested to know that in any of the frequency hopping spread spectrum communications they use, you can implement this using a linear feedback shift register. So this is another great example that doesn't require any DSP, wireless comms, something that takes kind of abstract concepts and makes it much more concrete, shows students this is something that's actually happening in the air around you right now. Another example that I've actually used with a group of K-12 STEM educators for the K-12 audience is just basic spectrum literacy. So learning how to locate ambient signals. I taught them, here's my car key actually. I taught them how to look up the FCC ID on the back of their car key, look it up in the FCC database, identify what frequency you expect to see that device transmitting on, and then pull up your waterfall plot and see if you can find that signal. And still with the car keys, when I teach network security and I have a week devoted to wireless security, I like to bring in some RTL SDRs, have them capture, lock, and unlock signals from their car key, and then see if you can decode these this is in Spectrum, see what security measures are in place for the car and how they can be defeated. So to summarize, there are so many ways to teach with SDR. I don't know if there's literally like 10 binary choices. I just picked 1024 out of a hat. But when you're teaching with SDR, there are a lot of decisions you'll make. You need to decide, what do your students need to learn about? Do they need to learn about radio architectures and pyramids? Do you want them to learn fundamental concepts in wireless comms? Are you just trying to get across some kind of unrelated concept where SDR might be a tool? What kind of skills do you need them to learn? Do you need them to program radio transceivers? Do you need them to be able to write DSP blocks? Or do they just need to kind of run experiments with a prepared radio and answer questions about it? Then you also have a lot of decisions about hardware and software. Are you able to achieve your curriculum goals with radios that are RX only, or do you need RX-TX transceivers? Are minimal specs okay, or do you need a kind of higher end radio? Then you have to think about how your students will access a radio. Are you going to give each student a radio? Are you going to set up an in-house lab? Or you can use a test bed. I personally am a big fan of test beds. I'll digress for a moment. There are a few open access test beds out there. One of them I operate, it's called YTest, but it's not nearly as good as the other ones. Orbit is at Rutgers and Powder Renew is at Utah. And these are basically, have these software compute devices, basically standard computers, radios, and other devices that you can reserve and then access over the internet. And this is really great because you can do like one-offs. You don't need your own lab space or equipment. You could just log in, do a quick experiment. Students can work on every hour of the day whenever they feel like working. And you as an instructor can prepare an environment for students to work on. I really like this because in an in-house lab where students are working on their own computers, they can do things that mess up the environment and kind of break it. And then you as an instructor spend a lot of time kind of debugging the environment. And of course, test beds come with facilities to kind of set up everything fresh at the beginning of an experiment. So that makes it much easier. Of course, there's that disadvantage, which is, it's a shared resource. So this is what the test bed reservation calendar looks like when someone who's using it or assigning assignments on it has an imminent deadline. And also it can be a little tricky to diagnose and deal with hardware problems. But I'm a big fan of test beds, and I'd love to talk to any of you about it in the session following the panel presentations. So what are my overall takeaways? Well, my overall takeaways are SDR is a fabulous tool for hands-on learning in every part of the STEM curriculum. I don't only use it in wireless comms, I don't only use it in DSP, I don't only use it in courses where students touch SDRs every week. You can use it in literally almost every course. I mean, if you're teaching programming, why not have an SDR assignment? I call it like a, kind of a gateway drug to wireless. So students touch these radios in their other coursework and they're like, hey, this is cool. I want to program some radios. Let's take wireless. Your students don't really need to program SDR in order to learn from them. And by that, I'm not referring to, block-based programming environments. I mean, even if they're just running prepared experiments where they change parameters, or even if you're just using some demos in class, that's also helpful. And along the same lines, students can use SDR in that way, even if they have no wireless or a signal processing background. And finally, my other main takeaway is you don't need your own hardware. You don't need a lab space, which sometimes is a lot more valuable than the hardware in order to teach with live SDR. So there are these open access test beds you can use. I'll show you an example right now. I'm currently logged into the Orbit testbed, and I'm going to go ahead and start a shiny SDR receiver. And let's see if my dangerous live demo will work. So now I'm taking a look at this radio receiver located in New Jersey. And I'll go ahead and do my frequency hopping spread spectrum script just for fun. So this is the kind of thing that you can do without any dedicated lab space or your own hardware. Stop that blank. So I think that's all from me. And I'd be happy to answer any of your questions later in the networking session. Thanks a lot.
Thank you. Thank you, Fraida. Very exciting. Very exciting. Yeah, and that's the thing. Like, I think until even the professor jumps in and does it, like, you know, even if it's a learning experience for them as much as it is for the students. But I think in some ways that's the best way of teaching, is how you taught yourself, then conveying it to the other. So that's so awesome. Thank you. Next up is Marc Lichtman. So take it away.
Can you hear me?
Yep.
Awesome. Let me share my presentation. Can you see that? Looks good. Okay, so my name is Marc Lichtman, and I teach a SDR class at the University of Maryland, College Park, within the computer science department. So today I'll briefly talk about my experiences doing that. It's a single semester course, and there's really nothing else about the CS department here that, you know, emphasizes signals or SDR. So we have to kind of start from the ground up. So the course overview, it's an elective, so it's not required. Only a very small fraction of the CS students here will take it, but it's meant to be very practical and hands-on. Most of them are about to wrap up their undergrad degree. Now they have little to no background in DSP and communications, as you might imagine, but they're very strong programmers. They have Python experience, especially, among other things. And the whole point of the course is to provide them with the necessary background by teaching just kind of the basic DSP theory and comms theory with as little math as possible. So using diagrams, animations, demos, code examples, like there's still going to be math there, but it's definitely not rigorous. And it's a lot less time consuming than the traditional approach that you might see like within a grad level of ECE, for example. And pretty much the whole course is just a bunch of topics that would each be their own courses within ECE, extremely watered down and condensed into one, because that's really the only way we would have time. And I try to make it as fun as possible because, you know, we want these students to enjoy it and possibly, you know, enter this industry when they graduate or even go into grad school. So if they don't have fun with their SDRs, then it almost feels like there was no point of the elective. So I try to make it fun and hands-on and as engaging as possible for them. So as we know, SDR builds on what I would consider multiple PhDs worth of foundational building blocks. And in my course, we certainly don't try to cover all of these. In fact, some of these we don't even really talk about at all. But this kind of, you know, shows the problem behind trying to teach SDR to students with almost no background in one semester. So it's definitely a challenge, going from nothing to ideally having them able to create an SDR application at the end of the semester. They may not have time to actually create the full application, but just, you know, the ability to, let's say. So several of the foundational topics that we have to cover first, really before I think that they can get very far, include just the idea of time domain signals in general. And we use audio as an analogy at the beginning. In fact, I'll use Audacity quite a bit. And then, you know, understanding the frequency domain. A lot of them don't have experience thinking in the frequency domain, which we really have to do. And then how to use FFTs in a practical sense, like why you have to, you know, FFT shift and what is magnitude, all that stuff. The idea of being able to fully sample a signal, you know, assuming infinite bits, if you sample fast enough, and then what happens if you don't, how anti-aliasing filters work. And then IQ sampling, one of the hardest topics, just because the SDR provides the signal at baseband, they don't know what baseband is at the beginning, or the notion of negative frequencies. So we try to explain that. And we go over kind of the basic like direct conversion SDR receiver architecture, which ties in pretty well with IQ sampling, quadrature sampling. Digital modulation is a really good one because we've covered a bunch of heavy topics. They probably didn't absorb everything, but then once we start getting into like actually modulating a carrier with data, the different shift keying schemes, QAM, I think it all starts to make more sense to them. And things start to come together. You know, we'll go over the idea of some number of samples per symbol when you're simulating signals, and then pulse shaping. You know, an important concept. We don't have too much time to get into it, and then we briefly talk about just noise, wireless channels, multipath. I do a little demo for them where I transmit a wide bandwidth signal around the classroom, and then kind of move the antenna around, wave my hands in front of it so they can see the the smearing and the holes in the spectrogram due to the frequency selective fading. So I think being able to actually see that like live is a really good introduction to the concept, because I know when I learned about it, it was all through math, and I don't think I fully understood it till I actually started working on projects after school ended. So I believe that without these foundational concepts, they're just not going to get very far with SDR. That's just my opinion. And the course also covers topics like cellular and IoT. We'll spend one day on each of them. In fact, we also had an optional lecture on electronic warfare for those interested. A lot of them ended up saying it was their favorite lecture. I'm in the DC area, so it's a very important. It's a an area that you see a lot. We also spend a little bit of time learning GNU Radio, as well as the SDR's Python API, which is pretty straightforward once we talk about how SDRs work and how tuning works and all that stuff. So why a CS course is a question I get a lot. You don't see this kind of thing in the CS department too often. But as we know, over the last decade, there's an increased surge in actual like professional work, either related to SDR or just DSP in general. And it tends to be very applied. So a lot of that work is very implementation heavy, involves a lot of software development, not as much mathematics, even though, it's the foundation. It just doesn't come in on a day-to-day at work. So I think because ECE, grad programs don't usually emphasize software development skills, there's a lot to say for CS students who are very strong programmers, and they really just need kind of that basic foundational knowledge to be able to, get a job in the area and contribute, pretty quickly. I think a lot of them don't, DSP and SDR is not in their mind. If they see a booth at a career fair from some related company, they might not even consider it. But after taking this course, they'll be able to interview very well compared to other CS students, at least related to wireless and SDR. So that's kind of the idea behind the course. Give them like the basic knowledge. Now, as part of the course, each student borrows a Pluto SDR for the semester. That's what we happen to have. And it ended up working out pretty well. They have an enormous frequency range after hacking it, which is pretty straightforward to do. And we mainly use them in a receive-only manner because we don't get far enough where I'm comfortable with them transmitting. And because it can receive up to 56 megahertz of bandwidth at once, even though that's not at 100% duty cycle because of the bottleneck of USB, it allows them to take snapshots of spectrum and create spectrograms that are 56 megahertz wide without having to retune. And I think that's valuable. You can do quite a bit. A lot of folks might think that USB 2.0 bottleneck is limiting, but I mean, they're using VMs as well. So there's a lot of limitations in terms of performance. Now, because we don't have that much time, we can't really get into full transceiver experiments anyway. So the focus ends up being more on spectrum sensing type of applications, trying to find signals, decode them, that kind of thing. We don't really get too deep into equalization and synchronization. Now, the students, they had an Ubuntu VM, but some of them had native installs. So that worked pretty well. They're CS students, so they're pretty familiar with setting up the software. And we gave them, a variety of antennas to use. And I think in general, for students that are totally new to SDR and DSP, it's valuable for them to have their own SDR that they can take home and use on their local machine. So that's kind of comparing to having them log into a test bed. But I think once they get that experience, they can definitely better use remote resources, like Fraida was talking about. And that's just my opinion. So luckily we were able to get each student a whole SDR for the semester. Now we use GNU Radio a little bit. I'm imagining most people here are already familiar with GNU Radio, so I won't go deep into it. But I will say it's been great for creating little demos. Like as a professor, actually trying to explain topics, I'll end up bringing out GNU Radio. And then in terms of in-class exercises, like where I might give them a flow graph that's maybe 90% complete or even 100%, but they have to modify it, it works very well. And I think for student projects especially, being able to take an existing GNU Radio application that functions so they can start from a point that works and then do something to it, either add to it or change it a little bit. They could start with like GRI IEEE 802.11 Wi-Fi based flow graphs and maybe pull out, information from headers. By being able to start from something functioning, they get a lot further, I think. Now I'll mention embedded Python blocks were extremely useful. Between them being able to upload their GRC file as a homework assignment and having that code already included. We do go over out of tree module creation, but I will say those embedded Python blocks were very nice. And they really only learned the basics of GNU Radio. We had 2 classes essentially and a couple homeworks. So it would have been nice to get a little deeper. Another thing we did as part of the class was mini capture the flag events. So about 2 to 3 times per semester, I spent 20 minutes at the beginning of class where I had a challenge for them. They had to either find a signal or decode it. That was kind of the theme. So they all sat there with their SDRs and laptops. And I tried to make them use like concepts they learned recently, as well as critical thinking. And it got them excited because these are CS students. A lot of them do like CTFs and other challenges on their own. So after those 20 minutes, I would share the solution to everybody because, only a fraction would figure it out. And I'll say the ones at the beginning of the semester are very challenging to design. So the very first one we did involved using GR Paint, which a lot of you may be familiar with. It takes a picture and then paints it onto the spectrum. So that if you're looking at like a waterfall or a spectrogram at the right frequencies, you'll see the picture. And it might be stretched based on your sample rates. But so the students had recently learned how to create a spectrogram in pure Python. That was actually an assignment they had. And I think that was a really good assignment. I gave them the signal and, told them what a spectrogram is and how to assemble the 2D array. So they were able to do it pretty well. And because they had this code, they could then use it for the CTF. And I'll say the CTFs were heavily inspired by the GNU Radio Conference CTFs. And at the bottom, that's an example of what I mean by decoding. We don't really get into full receiver, design. So they actually performed frequency synchronization on their own with a little slider in GNU Radio that controlled a frequency shift. So they essentially saw the real-time time domain plot as they shifted the slider, and they could see that overarching sinusoid start to disappear. And then I told them, just take a screenshot and try to pull out the ones and zeros. It's a little tough, but some of them managed. And then here's the example of GR Paint with the UMD mascot. And actually, in terms of figuring out who won, they had to email me the secret message. So that's why I chose the sign and the Phi-layer hackers message. And several of them got it. It was a pretty fun CTF. Got them excited. So that's all for the class. So I wanted to mention that after teaching the course twice, I created a free online textbook based on the course called pysdr.org. And the idea is it's like a guide to SDR and DSP using Python. There's a lot of topics there, but it's still a work in progress. And one way it differs from other resources is that there's no companion library like some textbooks use. It's just straight Python. So anyone who knows Python and doesn't know anything else about signals is kind of who this is meant for. So straight like NumPy, SciPy, Matplotlib, plus whatever SDR Python API you're using. So we have some examples using Pluto SDR, but they're kind of meant to be substituted easily. And it's very visual. There's a lot of diagrams. I try to minimize the amount of math, and it'll never be a hard copy because of the animations, but it's mainly meant to be a resource for my students and really anyone else who wants to use it. It's not meant to be like a moneymaker or anything. So if anyone's interested, now here's some visuals from the textbook if you're curious. And I've got some plans for future chapters like equalization and more actual SDR examples. So yeah, if you're interested in the textbook, definitely check it out and email me with comments or suggestions. I'm definitely interested. And I'll be presenting more about the course itself at ASEE this year. I think it's in July, but it's online. So with that, I will give it back to Cory or Alex.
Thank you, Marc. Thank you. Very insightful. In fact, that was a great resource that helped like sort of reboot the course I did like all in Python as well. Like, yeah, because of COVID, I'm not sure like, and this is something maybe a great question to ask during the network session. But if you had to teach your course remotely, did teaching it online change the dynamic? I think in Fraida, I guess in your case, because the students didn't have to buy the hardware, they could remote into testbed and do a lot of the stuff there. And then in Marc, in your case, I guess, because you have an online resource I saw, which was awesome, and it's in Python, students don't have to get like new hardware, new software or anything like that. But no, that was very good, very good. Thank you.
I will say we shipped the students SDRs last semester. I just sent them the USPS return labels, but it was easy enough to do.
Oh, you know, that's the thing, logistics. Oh boy, that's awesome. So with that, last but not least, is Cory Prust from Milwaukee School of Engineering and his experiences using software-defined radio in the classroom. Take it away, Cory.
Great. Thanks, Alex. So yeah, I just want to take a moment and thank Alex and the SDR-Boston folks. This is a great event. I feel really honored to be a part of it. And thanks to Fraida and Marc for your talks as well, which were really fascinating. I think you'll see a lot of common themes as I run through what I have to say. So I thought what I would share is just a little bit of my experience in teaching introductory communication systems courses using SDR-based laboratories. So just a really quick outline. I'll start with an overview of the courses themselves, really kind of focusing on this one introductory course. And then I'll talk about some of the considerations that I made in really designing and then deploying SDR-based laboratories. I'll give you a really quick snapshot of one of the labs. I'll talk about a frequency modulation lab and some of the different aspects that we've designed into that laboratory, a lot of which use SDR. And then I'll wrap up with a couple of lessons learned. So to kind of give you the context, I have two courses at our university that are using SDR-based labs. You can really just think of them generically as a first course and a second course. Most of what I'll talk about today is that first course. And this is really a principle of communication systems class. So think about a course that teaches basic introductory physical layer communications. So we go all the way back to kind of the traditional, analog modulation scheme. So AM and FM. In the second half of the course, we do get into digital communications. This is an undergraduate level course. It's senior level. and it's required for all the electrical engineering students at our institution. So that's 60 or 70 students a year take this course. They come in with a background in signals and systems, and they've seen Fourier series and Fourier transforms. We also have a probability theory prerequisite course, and that's mostly applied in the digital comms context, where we'll talk about bit error probability calculations, and that's pretty standard for this kind of a course. As far as the structure goes, we have 3 lecture hours a week and 2 lab hours per week, and that is a tightly integrated lab. We are very focused on, hands-on experience with the students. So under normal circumstances, they're physically coming to lab, and we're working with the students there. My institution is on a 10-week academic calendar. I guess I should feel lucky compared to Alex, who only has 7 weeks, so I shouldn't complain. But boy, it's really hard to get through all this stuff in 10 weeks. It's a really fast-paced course. Students find it pretty challenging. But in any case, that's the first course, really focused on fundamentals. We do now have a second course, which we've titled Software-Defined Radio, and we dive in deeper to SDRs and look at applications. In some sense, it's really a continuation of that first course, particularly in the digital comm area, where in the first course, we study basics of modulation schemes and IQ signaling. We do not get into synchronization and equalization and those kind of topics. We now save those for the second course. But again, I want to focus on this first course for the rest of my talk. So please keep in mind, these are students who don't have a communication systems background, and the goal here is really to get them to understand these fundamental concepts. I thought I'd quickly just go through a timeline to kind of let you know how I've arrived at where I am today. This goes back to 2013 for me, when I was teaching actually an entirely different course. It's a DSP elective course that I had a lot of flexibility in. I could try lots of different things. And about that time, I had started playing with RTL SDRs, and I thought it'd be really cool to do some projects with the students. So I got a bunch of RTL SDRs, gave them to all my students, and we did some projects. So they were viewing real world wireless signals. We're processing them in GNU radio, and there were really kind of 2 big outcomes for me back in 2013. One was just that experience for students of working with real world signals and processing them in GNU radio was just really engaging for students, and it was the kind of thing that I hadn't seen quite so much of in teaching other courses. But that work with real signals was just really engaging for them. And then the second big takeaway, I remember having some discussion at the end of the course with my students, and we were just kind of reflecting back on what we had done over the course of the term. And one of the students chimed in and said, hey, this is really great, but why don't you do this in the earlier course? That is, why don't you do this in that required communication systems course? And the student went on and said, I think I would have liked that course a whole lot better if you had introduced some of these topics there. And it's almost so obvious now thinking back to it. Yeah, it makes perfect sense, right? If we can get students working with real hardware and real signals, that might make that course a whole lot more exciting and more engaging to them. And so that led me down this path, which started in by introducing some demos into that first course. We did that the following year. 2015, we were able to kind of rearrange the lab experience a little bit to carve out basically a 2-week experience where we could bring some SDRs into the laboratory, give students at least some exposure. We felt even just that exposure to SDR was valuable and important. So we were able to craft that 2-week experience. We got some EDIS USRPs. We got some B200s. That we gave to students and let them basically play around with them for 2 weeks. We ended up using the MATLAB and Simulink interface, which has worked really well for us. One of the big motivators, even early on, is that I had just 2 weeks. So I wanted to use a software package that my students had some familiarity with. And so they come in with some MATLAB and Simulink background. And so that was really helpful to kind of get them going as quickly as possible. But then we come to 2018, and that's where I said, look, I think I want to change the whole lab experience in this first course. I think I can do it using SDR-based experiments. So I went through this process of redeveloping that. And we're now at the point where we've been running these labs for a couple of years. Students, I'll talk more about the setup in a little bit, but students can use RTL SDRs or Plutos. We have a couple of things that we still do with USRPs, but we've decided to stick in the MATLAB and Simulink environment. And I just do want to mention here, this entire set of course materials is freely available for anybody who wants to have a look at them or use them. They're posted out on the MATLAB courseware site. It's called Introductory Communication Systems Using SDR. The link at the top there will ultimately push you over to the MathWorks file exchange. You can download a zip file. You can see all the lab guides. All the Simulink models are there. And I just want to thank and acknowledge the folks at MathWorks who supported this. So their academic support team supported this effort. Mike McLernan and Daryl Lanebarger at MathWorks were my main contacts. So I'm really, really grateful for their help in doing this. So let me talk about design considerations. Being a first course, our focus is strong fundamentals, right? We want students to understand, AM, fundamentals of AM, fundamentals of FM, fundamentals of digital comm. And we really, being an integrated lab, we want to reinforce and in some ways extend that lecture material. So I really see SDRs as a vehicle here to help them develop that understanding, give them some practical experience. But also, to me, it's really about this engagement, right? I want to use this as a vehicle to engage students. And then that really leads to my second point. To me, this is really just a continuation of this trend we see, at least in electrical engineering education at the undergraduate level, where we're moving more towards mobile studio type laboratories. And for anybody who hasn't heard that term, really this is kind of about maybe replacing, at least in some instances, the traditional EE laboratory environment. Think of a traditional lab with benchtop equipment, oscilloscopes and power supplies and waveform generators. In some cases, we're replacing that with portable, low-cost USB devices. And in some cases, the devices are so inexpensive that students can buy them and own their own. And certainly that's true for things like RTL SDRs and even Pluto devices. So the idea here is that we can improve student access, both in terms of space, right? They can take this device and they can use it anywhere. They're no longer tethered to the physical laboratory. And then, as has been mentioned earlier, students can do experimentation anytime, which I think is really powerful. And so that's all been enabled by low-cost hardware and really powerful mature software packages. Another big consideration for us is how we're going to engage students. How are they actually going to use it? And I think there's opportunities to let students receive real-world RF signals. FM radio is a great example that you can do a lot with in an introductory communication systems course. Some of our experiments will involve instructors broadcasting signals in the laboratory and then students receiving that. And then we do some experiments where we have students transmit and receive their own wireless signals in the laboratory. And then the final thing I want to say, this has really become kind of a personal mission for me. I want to do anything I can to get students excited about this stuff. And you heard others say this as well. I think SDR is a great vehicle for getting students engaged and excited. Let me just quickly walk you through a little bit of one of our labs. So I'll talk about the frequency modulation lab, and I really want to start with the pre-lab experience. The fact that students might have their own RTL SDR, or we also ship them out to students during COVID here, but the fact that they have this, they have unlimited access, means that we can now rethink how students might do pre-lab experiments. So in this lab, we have students on their own before they come to lab build up a Simulink model to receive broadcast FM using their own SDR device. So if they get the model put together correctly, and we give them lots of guidance in terms of settings and configuring the model, but by the end of it, they'll be listening to FM radio in real time on their laptop. And I think that in and of itself can be a really engaging experience. We have them do other things as well. They look at signal spectrums, they measure bandwidths. We have an opportunity here to connect back to the course material. This is wideband FM, of course. So Carson's rule gives us a prediction for what that spectral bandwidth should be. So we can do some comparisons and connect, again, really, really closely to what's covered in the lecture content. Then we will also have in-lab experiences for the students. I'm a big proponent of simulations. So as a part of this lab, we have students construct a full baseband model of an FM transceiver, let them play around with signal parameters, let them play around with the influence of non-ideal effects. So I think in this model, it shows a phase and frequency offset. So we'll have them introduce a frequency offset in the signal, as well as noise in the model, just to help build their intuition about those kind of effects. And then I also do some instructor broadcast in this lab. I tend to do pretty simple FM signals, so things like tone modulated FM. Let them receive that. Let them do some analysis, maybe back out the modulation index, for example, using that broadcast. So again, just different ways of engaging them in the laboratory. And then in a lot of the labs, we end with a student project. And this is one that I like a whole lot. It's based on a real system. We basically designed this project around the automatic picture transmission system. This is deployed in, there's some old weather satellites at this point, but nonetheless, these are actual weather satellites that are up in orbit that broadcast this APT signal. And so we've developed a lab experience here where I can transmit an APT waveform. There's basically an image that's contained inside that signal. Students construct a receiver, and their goal in the end is to really just back out or reconstruct the image that's embedded inside that waveform. And so down there in the lower right, you can see that's one of the images that my students received. I also would do some mini field trips with my students related to this project. Where we'll go outside, and if you're out there at the right time of day with the right antenna and an RTL SDR, you can receive this satellite waveform. It's a little bit, it's sort of weather dependent here in Milwaukee. I teach this course in the winter sometimes in our winter term, so it's pretty cold to go outside and do this kind of field experiment, but sometimes we'll bundle up and we'll go out there and do that. And again, this can be a really, really engaging experience. So I'll wrap up here with just a couple lessons learned, and this is reiterating a lot of what, again, Marc and Fraida have already talked about. To me, maybe the biggest lesson learned is, I want my students to be successful. Their engagement in the course material is a major driver of that success. So in my case, given my constraints, really easy to use familiar software was pretty important. And that's kept us for right now with MATLAB and Simulink. I really like, putting the hardware in the hands of students, at least in this course. So, RTL SDRs are really inexpensive. I think having every student have that unlimited access is really valuable. And then, of course, experimenting with real world signals. I just think there's a lot that's motivating there for students. The last thing then, Fraida mentioned earlier, looking at key fobs, right? The signals coming out of key fobs. I do the same thing with my students. And invariably, that will bring up discussions with students about security of wireless signals and ethical use of SDRs. And so this makes a really nice context to have these really important discussions with students about these issues. And I didn't necessarily plan to do this. It just kind of seems to happen every time I teach the course. And I've really enjoyed having those discussions. And I think they're important for certainly the future of wireless engineers. So I will end here and be happy to answer questions over in the networking session. So thanks very much.
Okay. Excellent. Thank you, Cory. And you said one thing that really resonates very strongly with with me and like I think that's all of us, is that we're all very busy people. So I think very importantly is having a solution that is not only accessible to the students, but also very accessible to us, the faculty teaching them. So it's like, oh, I got to reinvent this. Yeah, 10 weeks, 7 weeks, 14 weeks. If you got to implement a communication platform to teach SDR and make it accessible, it's a very tricky thing to do. So let me first, so a couple of things. So first of all, thanks to Fraida, to Marc, and to Cory for again, their awesome insights on using software-defined radio in the classroom. I mean, that is really awesome. So, big round of applause. Virtual, I'm not sure if there's something in GatherTown where like the hands can do it. I don't think so, but very importantly, also, like, the lessons learned, it sounds like there's a lot of common themes or different ways of also going about this, but it does sound, compared to even like 10 or 15 or 20 years ago, we're in a much different environment than we were now than then. So it's great seeing that technology mature. So what we'll do now is we're going to shut down the Zoom session, and we'll all go into GatherTown exclusively until 3:30. But what we would like to do is try sort of the typical panel thing a little bit. Instead of going on the rugs, which are private discussion areas, what we'll try and do is we'll try and go into the what is it? Like an area that does not have any sort of like limitation in terms of how many people can fit in it, because the rugs are kind of on the small side, right? So if I look at eyeballing shucks.
So I think the problem with that is in the open space, you can only hear people right near you.
Oh, really? Can't go like 6, 7, 8 blocks away? Let me see. Yeah, so let little Alex go. There we go. So let's say next to the carpets where it says use arrow keys to move, to the left of that and slightly north, I think potentially we can.
See, like right now I'm pretty close to you, but I can't hear you or see you unless you get a little closer.
Okay, well we'll
we could all crowd.
Well, we'll try. It will look awkward in the environment, but at least everybody can interact. So how about we'll give that a try. So actually
I think it might actually work better if, so on the rugs, it's like a private space where you broadcast to the whole space. So if we're able to all fit on a rug, I think that would actually work better.
Oh, how? Like go to.
Like if everyone could squish onto the green rug.
Okay, so how about
it'll be a little squishy, but no, we're not going to fit.
No, we're not. Well,
actually, if you press the G button, then you could fit. You can like ghost behind people.
Oh, okay. Yeah.
So then we could like overlap.
Oh, okay. There we go.
But you'll have to tell people to do that.
Okay, so what I'll do is I'll make an announcement. Hey, everyone, go press G and then go in, and we'll go on one green rug. So, all right. So, perfect. Thank you, Fraida. Thank you. Again, we're learning this as we go. So
if you want some help setting up new SDR, I'd be happy to help.
Thank you. This is being recorded still. So, okay. Thank you. Okay. So with that, thank you again to panelists. We'll see you in GatherTown, and